This is a side-by-side comparison test with the standard maximum power point charge controller and a Tesla power amplifier with two identical solar panels. They're 230 watts, voltage maximum power 29.5, voltage open circuit 37.0, and a maximum power current of 7.8 amps. It's 12:35 on Wednesday. We're starting the test. Actually, we didn't hook it up when we started doing the measurements, but this is what it looks like with the 4-gauge wire connected to two 85 amp hour batteries in series for 24 volts to both the maximum power point charge controller by Seika and the Tesla power amplifier, the 30 amp version. Here's the voltage of A1, which is 12.25. A2 is 12.26. B1 is 12.25. And B2 is 12.25. A1 and A2 connected in series together is 24.50, and B1 and B2 connected in series together is 24.50, so they're both exactly matched on voltage. On specific gravity, we're measuring A1, and it's approximately about 1/8 of an inch into the red area on the hydrometer. All components are brand new, so that there is no variation between the components. The panels are new, the batteries are new, the halogen lights which are used for the load are new, everything is new, even the cables. They're all pretty much the same on the cells, about 1/8 of an inch into the red. That's on A1. This is battery A2. That's connected to the maximum power point charge controller by Seika, which can handle 12 or 24 volts. It's a German brand charge controller. About 30% more efficiency than the standard charge controllers because it tracks the maximum power point of the panel throughout the day. And all the cells are pretty much all about the same, about 1/8 of an inch into the red. Now this is battery B1. That's connected to the Tesla power amplifier. The weather's been typical northwest mixed weather. We had a lot of wind. It was cloudy in the morning. The wind blew away a lot of the clouds, so we got some clear sunshine as well. You notice on the specific gravities, it's just slightly better than the A banks. It's a little less into the red than the A bank. Now the B bank's been charged with the industrial rejuvenator several times on several cycles, so it's radiantly conditioned. The other one was charged with a standard battery charger, and so they were both brought to full charge and then brought back with the load. Here you can see the light pulsing away on the TPA. I connected the 20 megahertz scope into the input. You can see they're pulsing at about 1.219 hertz on the input. On the output, you can see the radiant pulses. This is only a 20 megahertz scope, so it's going up about 30 volts is all about you can see on this. Okay, almost, it's Thursday now, and it's about exactly 23 hours later. On battery A, we're getting 26.5. On battery A1, it's 13.26. Battery A2 is 13.26. Battery bank B, which is in series, is 25.86. Battery B1, 12.93 or 94. Battery B2 is 12.93. So battery A is winning at 26.51 and B at 25.86. Now here we're doing specific gravity on battery A1. And you can see it's right on the line between the white and the red. So again, the maximum power point charge controller that was connected to batteries A1 and A2 totaled a voltage of 26.51 volts, whereas batteries B1 and B2 connected to the Tesla power amplifier fell short at 25.86. Battery A2, approximately the same, right on the line between the white and the red. And here's battery B1 that's connected to the Tesla power amplifier. And specific gravity is just slightly less than the A bank. Pretty much right on the line between the white and the red, but just slightly into the red, which kind of reflects the voltage difference as well. Fairly close on specific gravity. This is battery B2. Now we're going to take these batteries down using identical set of new Sylvania halogen lamps that are perfectly matched, so they both draw the same amount of current, drawing about 4.28 amps on one. We're using one battery, of course, one battery bank, and then connecting the same lamp, different lamps, and we're getting 4.28 on those two, showing